we choose to go back to the moon and then on to Mars, and we're going to do it together.
This is Artemis II. Since 1972, it is the first time humans will travel beyond low Earth orbit. And every Artemis mission is designed to answer one question. Can humans operate, survive, and make decisions in deep space long enough to make Mars possible?
For every scenario, as we ride this amazing space launch system in the Orion spacecraft, 250,000 miles away, it's going to be amazing.
Artemis I, launched in November 2022, flew without a crew. Its job was to prove that NASA's new rocket and spacecraft could travel to lunar distance and survive re-entry from deep space. Artemis II is the first crewed mission, planned for 2026, depending on final readiness. The goal is to see 4 astronauts inside Orion and verify that the system works when lives depend on it. Artemis III is planned as the first lunar landing mission. 4 astronauts will fly to lunar orbit, and 2 are expected to descend to the surface. After that come Artemis IV, V, and beyond. Longer stays, permanent infrastructure, and sustained operations. So Artemis II sits at the pivot point. It's the bridge between testing machines and committing humans to live beyond Earth. Artemis is going the lunar South Pole. Near the moon's South Pole, there are regions that never see sunlight. Temperatures there are cold enough to trap water ice, possibly for billions of years. That water matters because it solves 3 problems at once. First, life support, drinking water and oxygen. Second, fuel production, hydrogen and oxygen for rockets. And third, sustainability, reducing dependence on constant resupply from Earth. In other words, the South Pole is interesting because it's useful. If humans are ever going to stay on the moon, or use it as a stepping stone to Mars, this is where it starts.
We hope it's not the dark side. We hope it's the lit far side, because that could mean that we could see parts of the moon that never have had human eyes lay upon them before.
When Orion returned from the moon during Artemis I, it survived re-entry. But when engineers examined the capsule, they noticed something unexpected. The heat shield didn't wear down in a perfectly smooth, predictable way. The material didn't behave exactly like the model said it should. And in human spaceflight, almost exactly is not good enough. The problem was how heat was distributed during re-entry. Orion doesn't dive straight into the atmosphere. It uses a technique called skip re-entry, briefly bouncing off the upper atmosphere to manage speed and heat. During Artemis I, that trajectory likely caused some regions of the heat shield to heat and cool unevenly. That can trap gases inside the protective layer, leading to cracking patterns engineers didn't fully predict. So NASA didn't replace the heat shield. They changed the physics of the re-entry itself. For Artemis II, the entry path has been adjusted to distribute heat more evenly across the shield and reduce those uncertainties. Artemis II will test that fix with 4 astronauts inside the capsule. That's why this mission isn't routine, and why engineers care so much about how Orion comes back, not how it leaves. One of the most important tests of Artemis II happens before the spacecraft heads to the moon. After Orion separates from its upper stage, the spacecraft turns back toward that stage. At first, Orion holds its position automatically. Then, control is handed over to the crew. At that point, Victor Glover manually flies Orion, guiding the spacecraft to within just a few meters of the discarded upper stage. Future missions depend on rendezvous and docking far from Earth. Crewed spacecraft will need to approach other vehicles, align precisely, and maneuver safely in close quarters, often far from Earth. You don't want the first time astronauts do that to be during a complex lunar landing mission. You want to test it early, deliberately, and while everything else is still simple. After additional checks, Orion performs the burn that actually commits the mission to lunar distance: translunar injection. This is the moment the mission leaves Earth orbit behind, enters deep space. From here, it's a multi-day coast toward the moon. When Orion reaches the moon, it performs a lunar flyby around the far side, the hemisphere you can never see from Earth. And during that pass, communication goes silent. The moon itself blocks the signal. For several minutes, there is no live voice, no instant feedback from mission control. The crew is alone with the spacecraft, operating entirely on their own decisions. This moment matters more than it sounds. Future lunar missions, and eventually Mars missions, cannot depend on constant guidance from Earth. Crews have to recognize situations, interpret what they're seeing, and act without waiting for instructions. After the flyby, Orion returns on a trajectory that brings it back to Earth. As re-entry approaches, Orion's service module separates, leaving the crew module to face the atmosphere alone. The capsule hits the upper atmosphere at extreme speed, 40,000 kilometers per hour, and the heat shield must do exactly what it was designed to do: sacrifice its surface in a controlled, predictable way to keep the inside survivable. If the capsule performs as expected, parachutes deploy in sequence, and Orion splashes down in the Pacific for recovery. 10 days after launch, the crew is back on Earth. If this mission works, NASA proves that humans can once again leave low Earth orbit, operate reliably in deep space, and return safely. But that's only the first layer of the story. Because Artemis II may also be the easiest mission in the entire Artemis program. What comes next involves far more complexity: lunar landers, multiple launches, precision rendezvous, and systems that must all work together. So the real question isn't whether Artemis II will succeed. It's whether success here is enough to make everything that follows actually work, and whether this path truly leads all the way to Mars.